So thank you for the kind introduction. And yes, we've been lucky that we got so much nice and good feedback already. I'm Jonas Heidrich, as Antonio mentioned, product line manager at Menhir Photonics. And today I would like to talk a bit about our oscillators for advanced timing and amplifier seeding. So if we look at a very simple example of an accelerator here in a linear form, it can be separated into three major sections. It's the particle source, often an electron gun, a photocathode, the accelerator part itself, and the end station where the experiments take place in the end. Of course, all these three parts, all parts in the accelerator need to be precisely synchronized. Menhir Photonics lasers are present in all of these three parts. The Menhir 1030 product line at 1 micron is present mainly in the particle source and also in the end stations for laser-based detection of individual beamlines, and also for our Menhir 1550 product line for the timing synchronization of all the devices in the accelerator, which what we've heard and has been super nicely described already by Cycles earlier today. Why are lasers quite often used in particle accelerators? This comes because we bring some advantages with our lasers. It's superior low noise performance, the repetition rate FREP, and also the carrier envelope offset phase FCO can be tuned. So we have actuators for that in the lasers, and it's a very reliable and easy to use plug and play system that has about the size of, I would say, a shoebox. A quick recap on what we are doing. And about the company, Menhir Photonics is a Swiss ultrafast laser manufacturer based in Zurich. We do the whole design and production in-house in our own ISO 4 clean room. And it's a fast-growing company that will reach more than 30 people this year, by the end of this year, which is soon. And this comes due to our values to produce robust and reliable femtosecond lasers that are turnkey and that will satisfy the people who use it. That's why many research facilities across the world, among them are DAISY, the PSI, CERN, SLAC, and so on, are trusting the Menhir 1550 and also the Menhir 1030 already. So why the oscillators? Of course, it's also about the performance of the oscillator itself. We provide repetition rates accessible from 40 megahertz up to 10 gigahertz, which is compared to other oscillators pretty high, with clean soliton pulses that are always below 250 femtoseconds and at wavelength at 1 and 1.55 micron. Here you also see that we get a very nice soliton spectrum at in this case, it's a 1030, but you can imagine that at 1550, it's the same. The laser is passively cooled, so no chiller is required. Here is a picture of an open box. We see that we are following a modular concept that allows to separate individual parts, which makes it easy to produce all these different systems on the same platform. Now I would like to use the remaining time to go a bit more into the details. Why are these lasers, or into the advantages of these type of lasers that I've summarized here one more time. If you look at the pulse train, so first we look at the low noise performance. So if you look at the pulse train of consecutive femtosecond pulses, we can have different sources of noise. It can be pulse energy noise, which is also called amplitude noise and results in different amount of energy from pulse to pulse. Also, or we can have timing noise, which is in the end is also known as the phase noise of the pulse envelope and will result in a different time where the pulse arises or arrives. If we look at the Menhir laser, we see that the the laser is itself already passively quite stable, so we have a very low pulse-to-pulse energy stability, a very high pulse-to-pulse energy stability, and high timing stability due to the innovative architecture that we use in the laser. This is not only enabling super precise measurements of in experiments or for amplifier seeding, but also the Menhir 1550 is ideal for timing distribution, what has been described before by cycles. We also have if you're more interested into that, we have a white paper about attosecond timing distribution available on our website, where the technology or the principle is described in more detail. Next, we not only have a very high passive stability of the laser system, but it also comes with repetition rate and carrier envelope offset phase actuators. This repetition rate actuator helps to lock to an external reference. Although the laser is quite stable on its own, it can be referenced to a maser or any other timing signal, so all the lasers. And the FCO actuator serves for tuning the carrier envelope offset frequency, which is needed for comp applications, where frequency comp, as Eduardo described before, is needed. This makes it, for example, the Menhir 1030 an ideal source for enhancement cavities. So you can take the laser and lock it to an enhancement cavity. And now I will advertise one more time that with the Menhir 1030, it was possible to, and an amplifier for sure, it was possible to get these more than 500 kilowatt average power, stable output power in the high finesse cavity. A very interesting publication that I can highly recommend to read. Lastly, the lasers are very, very practical, which is also good for the user in the end because it's easy to use. You don't need any water cooling. You just need 5 volts, 1 amp to put it on your laser table, and it's basically maintenance free. With this, I'm already almost at the end, but maybe a quick overview over the rep rates that we can do. So we have the lasers. Here is the repetition rate range, and the blue diamonds mark the standard laser products that we have. It comes with products from almost 100 megahertz up to 10 gigahertz. The lower area here, down to 40 megahertz, 40 and 80, which is often used so far, is accessible with a pulse picker that we also provide by now. And here, these hundreds of megahertz models are available in free space or fiber coupled, as the customer decides. We also, I want to emphasize that we provide multiple of the frequencies at what many particle accelerators are operated. So, for example, 54 megahertz or around 40 megahertz, which can be reliably produced in a very compact form and then pulse picked to the desired repetition rate. And we also can do higher repetition rates, 1, 1.3, 2.5, and more gigahertz. This at these two wavelengths, others are on demand. The pulse duration is always around 200 femtoseconds. And yes, as I said, high pulse-to-pulse energy stability and low timing jitter. I hope I could show a bit with this talk that we bring some key advantages with the femtosecond lasers for particle accelerators in the two product lines that we have at 1550 and 1030. And with this, I would like to thank you for the attention, and I'm open for questions. Thank you.
Thank you very much, Jonas. So we have time for questions. We saw the application of your lasers in the accelerator, but following the presentation from Roland, do you see also application in a facility like ELI? For example, where do you see your lasers that could work in this kind of extreme laser infrastructures?
Yes, I also wanted to at some point talk to Roland in a later stage. We are talking to Eli in Prague already, and we see that, or we think that we could provide a very good service for Eli, for both or all the three ELIs actually in the future, for seeding amplifiers if a reliable and low jitter laser is needed.
Mhm. I don't know if there is any other question or comment.